Let's go ahead and get started on chapter 4. We are going to be talking about linear functions. So a linear function is a function whose graph is going to make the shape of a line. So we've studied these before. It won't be any great new surprise. Remember that this here is function notation. The f of x just is a way of saying the y value. So it's the function with the variable, the independent variable of x, same as this. Y is dependent on x, and x is the independent variable. So in this equation, remember we have the slope here, that's the m. So m is the slope of the function, and which is a line, and that is rise over run. So it's the same in both formats. It's the coefficient on the x coordinate, or on the x variable. And then b is the y-intercept. And even though my math lab doesn't always put it in an ordered pair form, we prefer it to be as an ordered pair, 0, comma, b. Any function that is not linear is called nonlinear. I know mathematicians are so creative. So if it's not a line, they call it nonlinear. Only functions that are linear are going to have a constant average rate of change. So only linear functions have a constant, which means it's the same every time. Average rate of change. Average rate of change is a fancy word for slope. So average rate of change means slope. So also known as slope. And remember to find slope. We subtract the y's and then we subtract the x's. So the formula you've probably heard would be y2 minus y1 over x2 minus x1. So what we're going to do to determine if a set of ordered pairs like this table is linear or nonlinear is we're going to check the average rate of change, or the slope, between each two sets of ordered pairs that are like consecutive. And if it's the same each time, then it's going to be a linear function. So we'll do the slope between these 2 points. So we'll do -4 minus -26 over -1 minus -2. So that's going to give me a positive 22 over 1. So that's my slope, or average rate of change, will be 22. And then I check between these two ordered pairs. So 2 minus -4 over 0 minus -1, which is going to be 6 over 1. So 6. And what we're checking here is to see if our average rate of change is the same, which it is not. So, sorry, excuse me. Excuse me, I'm so sorry. My phone. It's probably going to go off again, so I apologize. Okay, so since the average rate of change is not constant, this is a non-linear function. So here, this is non-linear because the average rate of change is not constant. Average rate of change, remember, is just a fancy way of saying slope. So as soon as we get two that don't match, we can move on with our lives and say it's nonlinear. So let's check our next example here. So we're going to check our average rate of change. So the slope between 2 points. So we'll go 0 minus -4 over -1 minus -2. So that'll be 4 over 1. So our slope is 4, which is our average rate of change. We'll check these. So 4 minus 0 over 0 minus -1. 4 over 1. Okay, so far so good. Check these two. 8 minus 4 over 1 minus 0. 4 over 1. And then 12 minus 8 over 2 minus 1. So that's 4 over 1 as well. So we have a linear function right here because we have a constant rate of change. Average rate of change. There is a constant average rate of change. And they said that if it is a linear function, we should determine the slope. So the slope here is what we call the average rate of change, and that is going to be 4. Now, they could also ask us to find the equation for the line. And the easiest way to do that, like they already gave us the y-intercept of 0, 4. So we could just use the slope of 4 and the y-intercept of 4 to say that the equation of the line would be y equals 4x plus 4. But they may not ask us for the equation of the line, but just in case they do, we are ready for it. Okay, if our slope is positive, if the slope is positive, then a linear function is increasing over its entire domain. The domain for a linear function will be all real numbers or negative infinity to infinity. So if the slope is positive, that means it's going like slanting like that, which means the function is increasing everywhere. If the slope of the linear function is negative, that means our line is sloping in the negative direction from left to right, then that function is decreasing over its entire domain. And then we have another possibility because the slope could be 0. Now, a slope of 0 would be a horizontal line. And in that case, the function is not increasing or decreasing. It is constant over its entire domain. Okay. So let's look at an example. Here's our function, f of x equals negative 2/3 x plus 4. They want to know our average rate of change. Average rate of change, again, that's the slope. That's the number that's the coefficient of x. So it is negative 2/3. It never includes the x, it's just the coefficient. Now, since that slope is negative, this function is decreasing over its entire domain. Do you remember what we said that was a moment ago? The domain for a line we said was all real numbers. So in interval notation will be negative infinity to infinity. Now the y-intercept is the constant term at the end there. So that is this guy here. That's our y-intercept. It's positive 4. So as an ordered pair, we'll say 0, 4. Okay, now we need to look at solving some equations. We're going to solve them algebraically and we're going to solve them graphically. So I guess the first thing we should do is probably graph these two functions. So we'll graph f of x equals 4x minus 1. So that, of course, is a line. Its y-intercept is 0, negative 1. And its slope is 4. So we'll start with a y-intercept at 0, negative 1. And we'll use a slope of 4. So up 4 over 1, up 4 over 1. Or we could have gone down 4 and left 1. Okay. As long as we get that slope positively sloped. Oh, this one is not, that one's not in line very good. I'll just use these 3. We'll ignore that dot. Hopefully your dot is better. I'm sure it is. So that is my f of x. graph. Then I'm going to graph g of x. G of x is also a line. It has a y-intercept at 0, 5, and its slope is -2. So we'll go 0, 5, and then a slope of -2, so down 2 over 1, down 2 over 1. Okay, and that is g of x. So f of x on my graph is going to be that kind of turquoise blue color. G of x is going to be orange. Okay, so let's solve f of x equals 0. I want to talk about what that means in terms of what it looks like on the graph, and then what it looks like algebraically to solve it, because we want to be able to use both methods. Dig in for a pen. Okay. Algebraically, to solve f of x equals 0, all we need to do is take our function f of x, replace the letters f of x with a 0. So 0 equals 4x minus 1. And then we solve that. So we'll add 1 to both sides. So 1 equals 4x. Divide both sides by 4. So x equals 1/4. So solution to that algebraically would be x equals 1/4. Using the graph, f of x equals 0, that means that when y equals 0, what is x? So we're looking for where y equals 0. Y equals 0 is this axis here. And so when y equals 0 on this graph is going to be right here on the blue graph. So we're looking for the x-intercept. If it's labeled for us, we can get that. If it's on like a nice number. If it's not, like, we're going to have to just estimate this at 1/4. Hopefully we'd estimate it at 1/4. But that's how we would do it using the graph. Okay, algebraically, what does it mean for f of x to be greater than 0? Well, algebraically, that's pretty easy. We take our function f of x, 4x minus 1, and we set it greater than 0. We solve that, so add your 1 over. 4x is greater than 1. Divide by 4. X is greater than 1/4. Graphically, what does that mean? Graphically, f of x being greater than 0 means that the graph is above the y-axis, x-axis, above the x-axis. Okay, so let's look at that. So we previously had found the x-intercept of 1/4. So I would be looking at my blue graph, and I would say that is above the x-axis when x is 1/4 and every place after that. Except for I cannot include 1/4 because that's where it's on the x-axis. So when it says greater than, I would not want to include the value of the x-intercept. Because the value of the x-intercept would be where it's equal to 0, and we're looking for where it's greater than 0. And then we would want to use interval notation to answer that. So let's go back over interval notation. Let's go back over to our x is greater than 1/4 and put that in interval notation. So that would be from 1/4 to infinity. Or, I mean, they may want it in set builder. I prefer interval notation. But if they wanted set builder, we'd say x. So the set of all numbers x such that x is greater than 1/4, like that. Okay, what about f of x equals g of x? Okay, f of x equals g of x. So for f of x equals g of x, algebraically, we'll just set the two equations equal to each other. So 4x minus 1 equals negative 2x plus 5. And then we'll solve that. So I might add 2x over, so I get 6x. Add 1 over, so 6x equals 6. Divide both sides by 6, and get x equals 1. Well, on the graph, f of x equals g of x is going to be where the graphs intersect. So if I look at my graph, I can see that my graphs intersect right here. That order pair is 1, 3, but the answer that I'm looking for is going to be the x coordinate of that order pair. Okay. What about where f of x is less than g of x? So I know that f of x is equal to g of x right at this dot right here. So when I'm saying that f of x is less than or equal to g of x, I'm going to be looking for, oh, you guys, look what I did here. I labeled both of them g of x. I bet you were telling me that a long time ago. That guy is f of x. Man, I could really use somebody to like just be here while I'm doing notes to stop me when I make mistakes like that. So if you're willing to volunteer, let me know. So I'm going to be looking for where the blue graph is below the orange graph. Okay, so as I go along the blue graph, right here, like at negative infinity, see how the blue graph is down here and the orange graph is up here? The blue graph is still below the orange, blue is still below orange, blue is still below orange. Right here, they cross over, so they're equal to each other, and then they switch places. So now blue is above orange, blue is above orange, blue is above orange. So when f of x is less than or equal to g of x graphically, that means the graph of f of x, which in my picture is blue, is below or intersecting, since it said less than or equal, intersecting, pretend that says intersecting, the graph of g of x, which is the orange one. So we're going to want to give our answer in interval notation. Oh, goodness. Oh, goodness. Start again. Interval notation. There we go. So they are equal to each other right here at x equals 1. But if I cover up everywhere that after they switch, f of x is down below g of x from negative infinity all the way up until x equals 1. So I'm anticipating this answer to be negative infinity to 1 when I solve that. So I'll set up my inequality. F of x, which was 4x minus 1, is less than or equal to negative 2x plus 5. And then solve that. So add my 2x over 6x. Add my 1 is less than or equal to 6. Divide by 1. Divide by 6. X is less than or equal to 1. So that's what we had gotten. And of course, again, you could put that in set builder notation, the set of all values of x such that x is less than or equal to 1. Okay. Again, I will almost always prefer interval notation, and I will remind you of that. When you take a test for me, it'll say to use interval notation. Oh, and we already graphed it, so we can skip that step. Let's use the graph to solve. So we've got f of x equals 50. So remember that f of x means y, right? So this means y equals 50. So we're looking for the values of x that have a y value of 50. Since my ordered pairs are labeled on here, Here I've got my y value of 50 and my x is 40. So that's what I'm looking at there. So x equals 40 would be my answer there. Same kind of a problem. F of x equals 80. So I'm looking for a y value of 80. We're here. So x would be 88. And another problem almost just like it. F of x equals 0. F of x equals 0 means y equals 0. That's along here. That's this point. So negative 40 for the x value. Where would f of x be greater than 50? Okay, well, we already saw where y equals 50. So now I'm looking for where y is greater than 50. Goodness gracious, I'm getting a lot of notifications. I apologize for that. Let me put that on silent. Okay, that should do it. Sorry about that, guys. So here is where y equals 50, and I want my y values to be greater than 50. So I'm looking only at the part of the graph where y is greater than 50. So that is going to be from this y value forever in the upward direction. But of course, we're looking for a solution in terms of x. So all the x values starting at this x value and going towards infinity. That x value was 40. Since I can't include that ordered pair, that's an open circle because it was greater than 50. Those are going to be the x values that are greater than 40. I probably should have put x equals negative 40. So I'm just changing that to say i.e., like what that means is y is greater than 50. Okay. Where is f of x less than or equal to 88? So we already saw where x equaled 88. So where f of x is less than or equal to 80. We already saw where f of x equaled 80. So now we're looking for where y is less than or equal to 80. So here's where y equals 80. So we want it to be less than or equal to 80. So it's going to be all the y values below this point, including this point. Since we give that in terms of x, I'm only looking at the x values for where I can see this line. So that would be from negative infinity up to 88, or so negative infinity up to 88, or x is less than or equal to 88. Okay, where is f of x between 0 and 80, but not including 0 and 80? So f of x is my y value, so I'm looking for where the y value is between 0 and 80. So between here and here. So I'm looking at only this part of the function. So that would be my x values in between negative 40 and 88. So x values between negative 40 and 88, but not including them because those were open circles. So that would be negative 40 to 88 in interval notation, both with parentheses. Let's use this graph to solve where f of x equals g of x. So f of x is this slanty line. There's got to be a better word than slanty. Oblique line, how about that? That sounds more mathy. So here's f of x. So I'm wanting to know where is f of x, which is my blue graph, equal to g of x. G of x is going to be this one down here. So where is f of x equal to g of x? So what does that mean? Well, we looked at it a little bit ago, and to solve that graphically, that means where the two graphs intersect. So where do the graphs intersect? And then we're looking for the x value. Okay, so these two graphs intersect right here. at -6, -5. So the answer to that question would be x equals -6. Okay, oh, this is a good one. F of x is trapped between g of x and h of x. Okay, we haven't had h of x yet. Let's see. We can make h of x green. How about that? So I'm looking to figure out where my f of x, which was my blue line, is stuck in between h of x, which was the green line, and g of x, which was the orange line. So looking at that, I want to know where is f of x below the green line but above the orange line. So I'm looking for below the green and above the orange, and I'm looking on f of x. So I'm going to cover up everything that's below the orange and above the green because I'm looking for where it's between them. So then I'm looking for in between these two ordered pairs here. But remember that our answer is going to be our x values. So f of x is trapped in between g of x and h of x. For all the values of x that are between this x value of 5 and this x value of -6. So that are between -6 and +5. So in interval notation, that would be from -6 to, oops. Hey, you guys, did you notice that that was not a equal to? You probably did a long time ago. So that means those are going to be open circles, because if it was less than or equal to, they'd be closed circles. But since that's less than, it's going to be an open circle or a parenthesis right there. Okay, so just to clarify, this little symbol here means g of x is lower than or touching f of x. And then this symbol means f of x is lower than h of x, but not touching. So we're not going to include that intersection. Okay, what do we have next? Oh, we got some story problems. I mean, if you want to pause and come back and do story problems later, go for it. I'm just going to power through because it's like 4:15. I think I can get this done in 10-15 minutes and then go home. So straight line depreciation. So in straight line depreciation, it's like you just say you buy a tractor for your company, and then you say, okay, well, I'm going to depreciate this over 10 years. So let's say I bought it for $50,000. Then at the end of 10 years, it's going to be worth $0. So I would take the purchase price of $50,000 and divide it by 10, and that would be $5,000 per year that I would depreciate the value of that purchase. So that's what we're looking at here. Book value is the value of an asset that a company uses to create its balance sheet. Some companies depreciate assets using straight line depreciation so that the value of the asset declines by a fixed amount each year. The amount of the decline depends on the useful life that the company assigns to each asset. Suppose a company just purchased a fleet of new cars for its sales force at a cost of $31,500 per car. The company chooses to depreciate each vehicle using the straight line method over 7 years. So that means that each year the car will depreciate by the purchase price divided by the number of years we're depreciating it, so $4,500 per year. Then we're going to use a linear function that expresses the book value V of each car as a function of its age T in years. So if you think about the current value of an item is going to be, so the value of our item is going to be the original value or what we paid for it. And then each year, we're going to subtract a certain amount. So we would take the amount we're going to subtract, which we found by taking the original value divided by the number of, like the depreciation years. I don't know what they call that. Depreciation time. And then times the number of years that have gone by. So in our problem here, the value v of our function, of our car, is going to be the original value, 31,500, minus the original value, 31,500, divided by the depreciation timeline, which is 7, times the number of years past, which is going to be, oh, they said x for the number of years. I thought that was a t. So that's going to be our model. V equals 31,500 minus that simplified to 4,500x. So that is A in our problem there. B was to graph the linear function. So when we graph this linear function, I don't know that I'm going to have like a super amount of room here. When I graph this, my y-intercept is going to be 31,500. So 0, 31,500. And then my slope is going to be negative 4,500. So I'm just going to leave that graph up to your discretion to graph on your paper or not, because I think we know how to graph that. And I don't really have space on my paper. So I'm going to go on to C. What is the book value of each car after 3 years? So after 3 years, that means x equals 3 in our model. So we would just sub in 3 for x. So the value would be 31,500 minus 4,500 times 3, whatever that would be. I know you know how to do that in your calculator, so I'm not going to take our time to do that. Interpret the slope. Okay, let's look at that. Interpret the slope. So our slope was the 31,500 divided by 7. So it was 31,500 divided by 7, which was 4,500 over 1. So the 4,500, it was negative actually. So here we go. Slope equals negative 4,500, and that unit was dollars per, like over 1, negative 4,500 over $1, and the 1 was years, because we did dollars divided by years, right, up here. So negative $4,500 over 1 year. So that means that the value of each car, since it's negative, that means it decreases by that 4,500. Try and fit a 4 in there. 4,500 each year. E. When will the book value of each car be 9,000? So V is the book value. So we'll replace the 9,000 for the V equals 31,500 minus 4,500x, and then solve for x. So subtract 31,500, divide by 4,500. Okay. And I want to add a new one on there. I want to add F. What is the implied domain? So we've talked about the domain for a line. We said the domain for a line is all real numbers, which it should be. I mean, if we graph this line, it would go on forever in both directions. But the x values have meaning in this problem. The x values represent time. So we would want to restrict our x values. We wouldn't want time to be negative, so we'd say x has to be greater than or equal to 0, like that. But then remember what's going to happen. since we're depreciating it, the entire amount over the course of 7 years, at the end of 7 years, that car is going to be worth $0. And we're not going to own something that's worth negative money. So we would say that the implied domain would be between 0 years and 7 years, or 0 to 7 in interval notation. Okay, let's talk about supply and demand. I'm not sure if you guys have gotten to this in econ yet, but when we look at supply and demand curves, what we're looking at is usually the price along the x-coordinate and the quantity produced along the y-coordinate. So in general, if you are a supplier, the higher the price you're able to charge, the more that you want to produce. So generally your supply curve is going to be positive because the more something sells for, the more you're willing to produce. So here we have price per item and quantity produced or sold along the y-axis. So this is our supply curve. Then the demand curve kind of does the opposite, because when the price is high, people are not willing to purchase as many as when the price is lower. So our supply curve is generally positively sloped, and our demand curve is generally negatively sloped. And you're most likely going to be only working in this first quadrant anyway, but that's what happens there. And then we get to a point in the curve where those two cross. And that's kind of like, that's the sweet spot that you want to be at, because then you're not producing more than you can sell, and you're not, people are not wanting to buy more than is available. So we call this the equilibrium point. And that's where supply and demand are balanced out. And the ordered pair that's at that equilibrium point, the x-coordinate is going to be the equilibrium price, and the y-coordinate is going to be the equilibrium quantity. So this ordered pair is going to be the ideal price that you want to sell and the number of items that you can sell at that price. So over here we've got the quantity supplied of a good. So they've given us a supply function. That's this guy that I roughly graphed over there. Notice it has a positive slope. And then they've given us a demand function, which has a negative slope, and I've roughly graphed that one as well. They want us to find the equilibrium price, which is defined as the price at which quantity supplied equals quantity demanded. That is, the equilibrium price is the price at which the supply quantity is equal to the demand quantity. So we're going to find the equilibrium price of cell phones, and we want to say, what is the equilibrium quantity? So to do that, we're essentially going to be solving that equation, S of P equals D of P. So we can just set these two functions equal to each other. So 60p minus 900 equals negative 15p plus 2,850. And we saw how to solve those. We've solved those a lot, so I don't think we need to work on that together. Then it's asking us to find the price for which quantity supplied is greater than quantity demanded. So greater than quantity demanded, we're just going to take our supply of 60p minus 900 is greater than the quantity demanded. I think we can handle that. And then we solve that as well. And then they asked us to graph and label the equilibrium point. We kind of did that. But that's how we're going about the supply and demand type of problems. And that's an application of algebraically solving where two functions intersect and where they are greater or smaller than each other. Truck rentals. The cost C in dollars of a one-day truck rental is modeled by this function c of x equals 0.35x plus 45, where x is the number of miles driven. So then they want you to answer a few questions. What is the cost if you drive x equals 40 miles? So that's a pretty low level, like an entry level question. If x is 40, then the cost would be c of 40, which means that we should just sub in 40 for x and work through that. Okay, then kind of the next step, if the cost of renting is 108, how many miles did you drive? So then we're looking at the cost being 108, and we want to solve for the number of miles driven. Again, I think we can all handle that. Suppose you want the cost to be no more than 150. So I want my cost to be either $150 or lower. So the cost will be less than or equal to 150. Well, the cost is this equation here. Well, that function or expression. So 0.35x plus 45 needs to be less than or equal to 150. And then we'll be able to figure out the maximum number of miles we could drive. Now, implied domain, I'm not really, like, that one's a little bit more challenging because although the domain for a function that's a line, a linear function, is all real numbers, since x is the number of miles driven and it's for a one-day truck rental, I mean, obviously x is going to have to be greater than or equal to 0, but there's going to come some time, like, you can't just drive an infinite number of miles. So you might say, like, it might be 0 to infinity, but I don't think you can drive an infinite number of miles in a day. I mean, that's not a question that I would particularly ask you. I'm not sure what they had in mind for the answer on that. If you get a question like that, I would be really interested to see what answer they had for it. But mostly, I just wanted to show you how you can use these functions to set them up either by plugging in or setting equal to or less than. So that is what we have on section 4.1.